how dopamine works and how it plays a major role in neurodivergence, trauma, and addiction. Dopamine is often described as the brain's pleasure chemical, but it actually plays a bigger role in motivation, learning, and deciding what matters. In this presentation, I'll show how dopamine works across 3 levels: systems, neurochemical, and neuroanatomical, and how disruptions in this system are linked to ADHD, trauma, addiction, and autism. These regions form a connected network. The VTA produces dopamine, which is sent to the nucleus accumbens and striatum to influence reward and behavior, while the prefrontal cortex uses dopamine signals for attention and decision-making. At the systems level, dopamine links motivation, reward, and learning. The mesolimbic pathway, which connects the ventral tegmental area to the nucleus accumbens, drives reward and reinforcement. The mesocortical pathway supports executive function and travels from the ventral tegmental area to the prefrontal cortex. The nigrostriatal pathway connects the substantia nigra pars compacta to the dorsal striatum and governs action and habit formation. And lastly, the tubero-infundibular pathway, which runs from the arcuate nucleus in the hypothalamus to the anterior of the pituitary, mainly regulates endocrine function as a hormone inhibitor. These systems work together to determine what is important and how we respond to it. At the neurochemical level, dopamine function depends on how much is released, how quickly it is reabsorbed by transporters, and how strongly it binds to receptors. These receptor sites can be observed with positron emission topography or PET scans. Disorders are often linked to altered receptor availability or dysregulated release patterns rather than simply low dopamine. In ADHD, dopamine dysfunction primarily affects motivation and reward processing. Individuals with ADHD often show reduced sensitivity to reward and difficulty with delayed gratification, meaning tasks that are not immediately rewarding are harder to engage with. Research shows alterations in dopamine receptor availability, particularly D2 and D3 receptors, as well as differences in dopamine transporter function, which affects how dopamine is cleared from the synapse. PET imaging studies have found reduced dopamine activity in the ventral striatum, nucleus accumbens, and midbrain, key regions of the brain's reward system. fMRI studies also show reduced activation in the ventral striatum during reward anticipation. In addiction, dopamine systems become overstimulated by repeated drug use. Drugs hijack the reward system, making them more salient than natural rewards. Repeated dopamine surges lead to long-term downregulation, including reduced D2 receptor availability and blunted dopamine release. PET imaging shows reduced dopamine receptor availability in the striatum, along with decreased activity in the orbitofrontal cortex, which contributes to impaired decision-making and compulsive behavior. Trauma and addiction overlap in the brain's reward circuitry. Repeated stress and substance use can both disrupt dopamine signaling in pathways tied to reward, motivation, and reinforcement, which helps explain why trauma can increase vulnerability to addiction and why the two conditions so often co-occur. In PTSD, dopamine dysfunction affects both reward and stress systems. The brain becomes biased toward threat and survival, while reward processing is reduced. Dopamine signaling becomes dysregulated, particularly in how the brain responds to positive outcomes. fMRI studies show reduced activation in the ventral striatum and prefrontal cortex during reward tasks, which may contribute to symptoms like emotional numbing and reduced motivation. Trauma disrupts the brain's reward circuitry. In autism, dopamine differences are strongly linked to reward processing, especially social reward. The reward system responds differently to incentives, which may affect motivation for social interaction. A key PET/fMRI study found reduced phasic dopamine release during reward processing. This reduced dopamine activity was observed in the putamen and caudate, key parts of the striatum, along with altered functional connectivity across reward-related brain networks. All of these conditions involve the same dopamine system, but with different patterns of disruption. Dopamine acts as the brain's teaching signal, shaping motivation and behavior. When this system is altered, whether reduced, overactivated, or dysregulated, it leads to different psychological and behavioral outcomes.